Hello, let's today have one more lecture on the fundamentals and biomedical applications of quantum science and engineering. In the last lectures, we convinced ourselves that the mechanical behavior for particles, especially in the atomic structure, especially those particles that contain that makes the atoms, like the electrons, and even the protons and neutrons, they really behave like waves. That's the way to explain the stability of the atom. That's the way to explain many things we observe in nature, like the diffraction of electrons, right? Diffraction is a phenomenon that belongs to waves, but the electrons, they do show that out. So they must have that behavior. And thanks to de Broglie, we came with an analogy because, you know, the whole thing starts in the radiation. And from the radiation, we understood that waves, normally the electromagnetic radiation, had to be considered as packages of energy and momentum, which are the photons. So once we consider the photons, which are like light particles, we made the connection. And then we start to check nature in different aspects and find out that actually the wave description for the particles could explain the micro world, could explain the atomic world, could explain things that we could not explain just with the traditional classical mechanics. Okay, so today we're gonna give one step further and use those concepts and try to end with an equation that's the most general equation or the most fundamental thing of the quantum mechanics, which is this Schrödinger equation or wave equation. The same way that in classical mechanics we call the equation like the motion equation to determine what is the trajectory and everything when a collection of external forces or internal forces acts on some object. Now we're going to deal with the with the wave equation, and equivalently, instead of determine the trajectory, which is the traditional things we do in classical mechanics, right? Because determining r of t for a particle or a system of particles, we can get everything else. Now we're gonna get the wave function. And the wave function, and normally it's traditional to use the Greek letter psi. So we use psi because historically they use psi. Sometimes we flip to phi, but psi from now on will be basically the wave function. And there are ways of using what we know and things that we know must be true to put together the equation that determines the wave function. Okay, so the wave function, as we have done before, it must have some conditions, right? Because you see, depending on the physical system, depending on the conditions, depending on the potential energy, this potential energy is everything in the quantum system. So as the system is kept together by the potential and the interaction between the particles is the most important conditions of a physical system. That's normally what determines the behavior, how the system will show up, what's the properties of the system. And that's true even when we observe the macroscopic world, right? We all know that atoms that stick together strongly make strong materials. And atoms that stick together not so strongly, they can easily be dissolved by water, or they can be weak in general with respect to mechanical properties. So everything is in this wave function somehow, and we must know this wave function, right? And everything depends, the wave function depends a lot on the conditions of your physical system. Normally the conditions and the boundary conditions has to be matched. So this wave, as we did in the atom, that the electron actually is a wave going around the nuclei, like a stationary wave, is a matching of the boundary conditions, right? So what we have done so far using those concepts is that we test in simple system. Simple system means, those experiments that people has done, like diffraction of the electron, we are talking, of course, we are going the opposite. We are going to the massive particles to behave like wave, right? Very simple cases, we were able to do okay in explaining. Periodic motion, we learned the Wilson-Sommerfeld quantization condition, which is basically a way to match the wave, right? And HH or H bar, because it's the Planck's constant, is the dimension, is the size of the quantum world, more or less. That's give us a scale for the domain of the quantum world. But, we tried that in the last lectures and works perfectly. But we still do not have a generic situation. We could not deal with a generic. I remember I explained to you using the uncertain principle, the ground state energy of the harmonic oscillator. But to really get the conditions of the harmonic oscillator or any other situation in nature, we needed to have a generic way of looking. We cannot only look into simple system where we can use the de Broglie wave, or periodic systems where we can do the integral of u dx, and that's an integer number of h. We cannot do that. We have done this, but this is not a generalized way of doing. Today we're going to generalize it, so we hope to end with a condition for this wave function that actually represents the physical system. And more than that, we have to learn how to extract the physical properties of the wave function. The wave function must have all the properties of the system, and we must extract from that all those properties. We have to learn to do that. Okay, so just to refresh your mind, we have this wave behavior, and normally the energy is related to the frequency, and that allow us to quantize the boundary. If you have a bounded system, if you have a system that's confined, it's localized, the conditions where the frequency or waves can exist in this situation, it's discrete, like the wave in a string or the particle in a box, the way we solve it, because of the conditions that we have at the walls. That means energy is quantized, right? And of course, the spatial part is related to the momentum of the particle. So those are the situation, those are the conditions that we're going to do. And let's use everything we learn and some truth on physics, which is the energy. The energy is composed of many parts. We know that. Energy can be located in different degrees of freedom. It can be in the potential energy, or it can be in the kinetic part. So using that, we must build up. We're not going to deduce, we're going to put together what we call the master equation for the quantum phenomena that we're going to use from there on. Okay. Well, everything starts when Erwin Schrödinger, a guy from Austria, that he long ago, right, about 100 years ago, he was able to study all this, looking to the aspects of the de Broglie wave, and he was being able to make a formulation or come with a hypothesis that he believes was the fundamental hypothesis of quantum mechanics, and a generic way of solving the problem. So that's why we call that equation that we're going to come and present it to you as Schrödinger equation. And this guy really was able to, by looking to the aspects of the de Broglie wave, right? So he looks to the aspects of the de Broglie wave. He came with a generic equation. And that generic equation is a kind of formalization of quantum mechanics. So that's what we're looking for. So how can we have a generic way that we can apply for any physical system, from free particles to bounded system to scattering problems to anything we want, and then try to come with an interpretation of this wave and seeing the limits of validity of those things. Okay, you know, and I told you in the very beginning of this course that when we improve a theory, we never destroy what we had before. In general, we have to have a theory that does not explain only a small fraction of phenomena. The theory is good when it explains something you're observing, and everything else you use it to explain before using different things. We cannot come with a theory that only explains the electron in the atom and does not explain everything else in the nature, right? So the theory we're looking for, which is the quantum mechanics, has to explain everything. Okay, so let's start, because what we have now is a massive particle. And even though the theory we're going to do, it works for light as well. But let's start with a particle. And as we know, when we're dealing with the particle, we normally refer to the energy and momentum. This is the two important things of the particle. And from there, we want to know how to get then from the wave. Suppose we have a wave function. So we have a wave function for a particle. And in fact, we already wrote before how should be if I have just a particle traveling in space, how that should be the plane wave for a particle. And from that, we should be able to extract whoever are the momentum and the energy of the particle. Let's start from this point. Let's start by seeing how energy and momentum is carried inside the wave function. Even though we don't know how to determine the wave function in a generic way, but that doesn't matter. We start that way. As we discussed before, if we consider a free particle, free, which means the only energy is the kinetic energy. So the only energy we have is p squared over 2m, is the kinetic energy. Then the particle with energy and momentum, which is well characterized by that relation, it must have, following everything we learned, following the de Broglie hypothesis and everything, we propose for this a wave. And in fact, we use this wave to test many things, including the diffraction. Normally, I work with sine or cosine for a plane wave. But we're going to see soon that the combination of them is the ideal situation. So suppose we have this momentum and we have the energy. Associate with the momentum, we have the spatial variation. And associate with the energy, we have the time variation. And then the best wave for this, right, is a plane wave. It's a free particle, it's everywhere in space, is a plane wave. We already discussed this aspect. Now, there are some interesting things. Suppose I give it to you the plane wave, which is the wave function that represents the particle. Of course, you have to come in and know exactly from there how to extract the momentum and the energy, because those are the two things that characterize this particle. And as I already insistently told you along the lectures, the momentum is here, is on the spatial part, and the energy is in the time part. right? And the oscillation represents the wave. Now, let's, when you want to understand how anything varies in space, what do? You take the derivative. If the derivative is 0, means this does not vary in space. If this does not vary in space, it's because there is no oscillation, because lambda means the periodicity of the spatial variation. Right? Okay. So let's take, we took as a wave function an amplitude times the sine of 2 pi x divided by lambda minus 2 pi nu t. Normally we characterize this by omega, this thing here we characterize by omega, and this we characterize by k. But I kept it that way to be clear now, right? And as you know, this is a traveling wave, which travels with a velocity that we studied before. So I took something that's not a localized particle, it's a free particle, plane wave, we don't know, it's everywhere, right? We're gonna come to these measurement problems later. So as I told you, if you want to know how the spatial variation of the particle takes place, you take the derivative. So let's take the derivative of this wave function. Let's take the spatial derivative of the wave function. So ddx of this wave function. And I'm using partial derivative because it's depending on the time and the space. So we must consider the partial derivative in this case. So when I take the partial derivative of this wave function, it turns out that you all know how to do the derivation, right? The derivative of the sine is cosine. And then I have to derivate the argument. And the argument in this case gives you 2 pi lambda. So at the end, by doing the partial derivative with respect to x, which is the spatial variation of this wave function, it gives to us 2 pi divided by lambda times the oscillatory part. This oscillatory part continues to be a wave. You know, it's complete similar wave because a traveling wave, if I give you a traveling wave that's represented by a sine or a cosine, you're not going to be able to identify because they only differ by a phase, by, you know, advancing or retardation. So they are basically the same in space, which is the thing. So basically what we see here is when we do the partial derivative of the wave function, we get that this quantity is the wave which is there, but in front of the wave we have something related to the spatial variation, which is the lambda, of course. I mean, this is the purpose of doing the derivatives, to find out how is the spatial variation of the wave function. But we learned before that 2 pi divided by lambda is exactly, as we learned from the de Broglie principle, 2 pi divided by lambda is exactly the momentum divided by h. Remember, we have a lambda equal to h divided by momentum. Therefore, you know, that's the lambda. 1 over lambda is just reverse this relation. This is the de Broglie wave, that we are dealing with a wave function for a de Broglie wave of a particle. So 2 pi divided by lambda is the momentum actually, divided by h, by the Planck constants. So what's happened is that by taking the spatial derivative of the wave function that represents the particle, we get the momentum, as we knew before, because we keep telling you that the momentum is associated with the spatial variation. So that's a very important statement, because if I have the wave function, I know a mathematical operation that can give me the momentum, is the space derivative, and that's proportional to the momentum. With some constants, of course, because, you know, to really be the momentum, you know, we have to multiply by h, the 2 pi is not so important here, or then we include the 2 pi here, and then basically we're going to multiply by h bar. That's normally what you do. So that's why I said with constants here, because taking the derivative, if we really want the momentum, we should add something here, that constants. That's what we're going to do later on. That's an important thing to keep in mind. By doing the spatial derivative of the wave function, I'm getting the momentum. Right? Okay, now let's do the time derivative. Let's do the time derivative. When we do the time derivative, it's the same. What we get in front of it is the frequency. But we learned that 2 pi, the frequency, is the energy divided by h. Therefore, the time derivative of the wave function, oh, there is a sign here, but don't worry about the sign now. This is not the important fact. I could say that minus the derivative give you the energy. So again, by doing the time derivative, we get the energy times the wave, times the oscillatory part that continues to be wave. But if we remove this part from the derivative, we end with the energy. So the time variation of the wave function is the energy, as we said before, because the energy is related to the frequency. But if we have the wave function, we take the time derivative, and the time derivative is proportional to the energy. That's for sure. There are constants again that must be here, but for this example we took, which is the plane wave, doing the time derivative, we get the energy. So you see, there are two things we learn here. The spatial derivative is like momentum, and the time derivative is like the energy. But if you are interested in this, in the p square, which normally is the relation between energy and the kinetic part and the momentum for this free particle, we must do the second derivative, because if I do the second derivative of the wave function, like here, I took one derivative. If I take the second derivative, these things will come back. There will be a minus sign, but don't worry about the minus sign now. But then I will have 2 pi divided by lambda square. And 2 pi divided by lambda square is just this thing's square. So 2 pi divided by lambda square will be p squared divided by h bar, because I put this 2 pi here. So h bar p squared divided by h bar square. That's why we're going to end up by doing the second derivative. So for this free particle, and from the properties we know, if you don't want to violate anything, if we want to keep the idea that energy has to be proportional to the momentum square, which is something that nobody questions, right? We must build up an equation that has the time derivative proportional to the second spatial derivative. Just because of this argument. This argument gives to us that since time derivative represents energy and spatial derivative represents momentum, whatever is the equation we're looking for this wave, because up to now we build up the wave in a band waving or in a simple way. We never really did it in a formal way. That's what we're trying to do now, a formal way. So that's the equation. Because you see, wave equation, if you learn when I explain to you wave equations, when I explain the past wave equation, you're going to see that there, the equation that determines the wave, like the electromagnetic wave or sound wave or any wave, we're going to have the second time derivative proportional to the second spatial derivative. But here is different. There was some attempt of constructing an equation based on those wave equations, based on the fact that the second derivative in time should be proportional or should be composed with the second derivative in space. But this violates this principle. Energy, which is the first derivative as we show, must be the second derivative of momentum, of space. So, because energy and momentum are related that way, I hope you're understanding that whatever is the equation that we want to put together, the first derivative of time should be composed with the second derivative of space, if we want to keep it that the energy of the particle is proportional to the p square. At least for the free wave, this is the truth. We cannot be different, right? If we have this, because the first derivative give you more or less the wave, but the coefficient now will be the energy, because the amplitude goes away, right? And the second derivative give you the momentum square. So they must be related, as we know from this proportionality. Okay, so this is an important thing. This is important because we are looking for an equation that has to be consistent with the fact that energy goes with momentum square in most of those physical systems. And then you're going to say, well, but relativistically speaking, that may not be the case. And I agree with you, but I am jumping a few steps that was done in the history of the formulation of the quantum mechanics, proving that that's the way that should be, because if I have a particle, in most of the things, we should... we never told you that when I put a particle in a box or I have a free particle, it should be relativistic to be behaving like wave. On the opposite, it has to have a momentum enough to show up a big wavelength compared with the structure to show up the wave nature. But we never rely on relativity particles to show the wave behavior, except when we go to photons. When we go to photons, they are naturally relativist massless particles. Then, I come with an important observation. Very important observation. First of all, you have to write and keep that in your heart, that physical quantities like momentum and energy are obtained from the wave function through mathematical operation. You already saw that. We're going to do a lot of mathematical operations on the wave function to get physical properties. In fact, quantum mechanics is built up on what we call operators. Operators are things that make a mathematical operation in the wave function. So this gives us the beginning of what we call operator algebra. That we're going to use a very slide this in the whole course. We're not going to stick to this as the main purpose of what we're going to do. But it is something important to keep in mind, because when you say that quantum mechanics is based in operators, normally we learn from the very beginning that mathematical operation apply to the wave function, give you the physical quantities. So therefore, the only way of really dealing with this algebra is through doing mathematical operations. And therefore, we call, instead of call the momentum, we call the momentum an operator, because it's going to operate on the wave function and give you the real value of the momentum, and so on with the energy and all the other quantities that we're going to learn. Angular momentum and everything, they have the equivalent properties in this sense. Once you have a wave function that we are looking for, you must somehow do mathematical operations on it to get the informations, physical informations on the system. So the wave function itself, it carries information, but it's not the information itself, right? Okay, it's important to know that the wave function, the physical meaning of the wave function is almost no important, except the square, as you're going to see. But the mathematical operations on the wave function, they have a physical meaning, and they must be, we must keep attention on them. Okay, so I gave it to you a plane wave, and I put sines or cosines, doesn't matter. Normally we combine these two. Well, if you remember the relation that E to the I theta is equal to cosines of theta plus I sine of theta. This is a very important relation. It has some names in mathematics, but doesn't matter, right? We know this relation. So always that we want to combine sines and cosines, we express as exponential of a complex argument. That's a traditional way of doing. And as you saw, I mean, we have sines and cosines are good solutions. You know, we sometimes chose sine and sometimes we chose cosines for simplicity. In fact, sines and cosines are both nice plane waves. So if both are nice plane waves, both must be solution of whatever is the equation that determines the wave. Therefore, we're going to combine them here. Instead of telling you that a free wave, a particle with determined momentum and energy, which is a plane wave, is just sine or cosine, we're going to combine them because that's the most general solution, right? As you learned from the beginning of the mechanics and solution of equations. So from now on, I'm going to use the wave function for this free particle as a combination of sines and cosines. I'm going to express this as A amplitude times exponential of I 2 pi lambda x minus 2 pi nu t. So this is actually cosine A times cosine of this argument plus I sine of this argument. And that's the most generic solution we have. And that's the way to do, okay? Believe me. Why this is normally convenient? Because any derivative of this repeats the function, right? The argument is the same, so if the I goes here or there, doesn't matter. So it's a nice way to deal with plane wave, expressing that in that way. And in engineering, we do that all the time. We like to do that all the time. But we must know that what we're doing is a combination of sines and cosines. What about the complex number that appears? This is not a case. It should not interfere in anything. In fact, the quantum mechanics will have a lot of complex numbers because that's the way of mathematically express the things. That's the way of mathematically use the wave function. So complex numbers is not anything to be worried about, because what will be physical is what we extract from there, right? It's not, we're not going to have a complex energy, or if we do, we must have a mathematical interpretation for that. And Normally we do, you know. If you learn how to use these things, complex numbers, in a good way, it is a wonderful tool, and it normally simplifies a lot the procedure that we have to do. Okay, so what's interesting here is that we all agree that we're going to use sines and cosines, because if both are solutions, the sum are solutions, right? And we are still dealing with a plane wave. So if we're dealing with a plane wave, that's the best way of expressing. And I hope you agree. Okay, if you agree with me, then let's take this wave function. And let's now take the spatial derivative. So we're going to use this wave function. And then now we take the spatial derivative. And to really have the momentum, you all know that the derivative of exponential is exponential, right? I hope everybody knows that. So the derivative of exponential is the exponential. And of course, then we take the derivative of the argument. So when we take the space derivative or the x derivative of this, we get the same thing times I 2 pi divided by lambda. And then I'm going to convert this. I take the 2 pi divided by lambda. This is like 2 pi p divided by h bar. I'm sorry, not 2 pi. This is like p divided by h bar, the way I showed you before. Here, 2 pi divided by lambda is actually taking this 2 pi from here, put here 2 pi underneath. This is what I call h bar. So 2 pi divided by lambda is p divided by h bar. H bar is the notation of h divided by 2 pi. So when I do this, what I end by having is the momentum divided by, and the I in front of it. So I divide by I, and I multiply by h, and what I have is p. So this is a real true situation, and you can verify yourself that taking the spatial derivative of the wave function that we just construct, it is h bar divided by I d dx of psi, which is the wave function, giving me p psi. Repeats the function. And I do it with the energy now. If I take the energy derivative, I'm going to have minus 2 pi nu in front of it and repeat the function. Then I have to get rid of this by, again, I have an I here. So I can write this as minus I h bar ddt of psi. And this is equal to the energy, because I'm going to use oni. I'm going to use that is energy divided by 2 pi times nu is the energy divided by h bar. Then I put the h bar on the other side, repeating the function. This is a mathematical verification that the momentum is now this quantity and the energy is this quantity. Okay, so if I have a free particle, I could build up now, because if I wanted to have the relation E equal to p squared divided by 2m, I could say that minus I h bar d dt of psi is equal to minus h bar square divided by 2m, because it's square, d2 dx2 psi. I could build this equation right here, and that represents that function. In fact, I can show to you that the solution of this function is this wave function. The solution of this equation is this wave function, because that's the way we build up, of course. Now, Let's go to a more generic situation. As I told you, a physical system is a system that has a potential and particle that can be in that potential. This is the most generic physical situation. And we're going to call this potential energy because the energy is made by the potential part and the kinetic part. And we all know from basic mechanics that the energy is the kinetic part, this is the kinetic part, plus the potential part. That's how we learned to solve any problem in mechanics. We have the kinetic part and we have the potential part. We already verified that this has to be consistent with what we know from the wave function. So if I have a wave function, psi, how I get the energy? Well, I just learned that the energy, if I have a wave function, this part, the energy is minus I h bar d dt of the wave function. This gives me the energy times the wave function. I learned that the kinetic part is just the second derivative of the wave function times minus h bar squared divided by 2m. That's the kinetic part times the wave function. And the potential energy. Well, the potential energy is just the potential energy times the wave function. If I take a wave function of a system and I want that this be true, that's the equation that I build up. Right? If I take that this is true for my physical system, the energy of the particle has to be the compromise between the kinetic and the potential part. And I know what is energy in terms of wave function, how I extract the energy from the wave function, how I extract the kinetic energy from the wave function, and of course the potential energy is just this. I could pass this on the other side, and then I tell you that I will have minus here and this, but that's the same, right? Doesn't change anything. So at least I came with a wave function or wave equation that is consistent with energy being the kinetic part plus the potential part. And what Schrödinger claims is that this is valid for any physical system. Because in any physical system, if you take from the total energy, the local potential energy, whatever is left is the kinetic energy. That's the truth. We know that. So he said it doesn't matter if it is free or not, even though I make the tests for the wave function of a free particle. It must be that this equation provides the wave function of any physical system represented by a particle in the presence of this potential. That's a very general statement. And this is what Schrödinger proposed to us. As you see, I did not deduce the equation. I induced the equation at the most. Right? And that is established to be the master equation for the wave mechanics, for the quantum mechanics. And we must now somehow we use this equation to explain many of the properties, to explain many of the situations that we have. Okay? And I just want to maybe emphasize that this equation is what we're going to use from now on to explain many things, but we got to get familiar with it. Because this equation is natural. Anybody that looks to this says, well, any particle that has some energy will travel between this point and this point. And if you have another energy, but see, any energy is possible. Okay, now here, no. Here is not any energy is possible. The only energy is possible is if the solution of this equation exists. If I have a psi that satisfies this equation for this condition, then the physical system exists. And then I'm going to find out that, it's not any situation. And by the way, I assume that the system is time independent, right? But sometimes it's not time independent. I already put the potential here that's not time independent. Normally it can be time independent, and this is the generalized equation. So if this is time independent, so this normally can be time independent, and therefore this is generalized equation. But this cannot be true always, or does not necessarily need to be true always. Most part of the time we have a kind of stationary, non-time independent potential. And in this case, this simplifies a lot, because time in this equation can be separate from the spatial part of it. And when we do that, we can get a special equation that is the time independent equation. But that I'm going to do in the next lecture, and continue with everything in the next lecture. See you then.